Okay, very nice. So I think we're done, and with this, let me share my screen. Okay, fine. So actually, yesterday we were discussing about Wilks' theorem. Let me just go back a little bit to the end of the lecture. No, so this is a thing of today. Yeah. So in summary, I think it is important to summarize, because the Wilks theorem is it's a very important and very popular tool for getting confidence intervals or regions. And it is important to know what you're doing, or what you're assuming is that your estimator there, and this theta hat, so you're assuming that they are distributed in a Gaussian way. So your maximum likelihood estimates are assumed to be distributed in this way, and consequently, when you compute this object, this statistic, you get in the large n limit, in the large sample limit, you get the chi-square distribution. I mean, this likelihood ratio is distributed as a chi-square. So, and then we put an example yesterday about it. So I will send you the notebook hopefully today, and so you may just digest it with more time. But it is important to know at least some cases where applying Wilks' theorem is not convenient. So so cases where Wilks' theorem doesn't apply. And the first case is a case where you have a few number of events. Because if you have a few number of events, let's, for example, imagine that you have some Poisson noise. You are really working with a low number of events, then it is quite unlikely that the conditions of the Wilks theorem will apply. So at some, in some sense, you would need to have a decent amount of data points, let's say, of number of events, if you want. The other situation where it is not applicable, the Wilks theorem, is imagine that, so suppose that your parameter, the one that you are estimating, may be a physical parameter, for example, a mass. Okay. So if you have a mass there, then of course the mass is positive, right? And then the distribution of your estimator of the mass, let me call it mass hat. I mean, if this is 0 here, then okay, you will have some distribution, but obviously this is not a Gaussian, so this part is not valid, it's not physical, so you don't want to estimate something below 0, right? And in this situation, also the Wilks theorem is breaking, let's say. And then another situation which is more difficult to see, another situation more difficult to see if you don't study like the proof of the Wilks theorem, but I'm not. I mean, this is going out of the scope of this lecture, and I encourage you to go to the books. I mean, I think it is in Cowan, the book, proof of the Wilks theorem. It's not difficult. It is just that it requires more tools that I'm not presenting now. And then you would see how this would break it. So it is a case where one of the parameters, for example, have very large variance. Because then having very large variance will actually make the parameter. So imagine you have a parameter here, a particular parameter here, and then the variance of this parameter is, I mean, like almost infinite. It's like almost flat. So in this situation, also you will have that the Wilks theorem is probably break it. Okay. So yeah, that was something that I wanted to say just to close the topic of the Wilks theorem, and then we go now to another topic.
Sorry, Brian, can I interrupt a second?
Yeah.
I don't really see very clearly the second point in your bullet list. In the case of a physical parameter, like, of course, I understand that mass needs to be positive, or if the parameter is a physical one, there might be some constraints that we, let's say, theoretically put on it due to physical reasons. But I don't understand why the theorem doesn't apply in that case. So I understand that your distribution needs to be from 0 to the right in that plot you drew. But I don't know. I think that's a constraint that we put like afterwards. Like your distribution would be on both sides of 0, and then you only accept, let's say, the values that are positive. I don't know if I'm explaining myself.
So you are asking about why it is not valid in the second case?
Yeah.
And in the second case, where the so what you're trying to let me see if I understand. You are saying that I can just propose a Gaussian distribution for this estimator of the mass, and then like cut it afterwards. This is what you're saying?
Yes.
Yeah, but this is actually, as I will comment in a second,
Okay.
this is actually not giving you the correct coverage if you do that.
Okay.
So yeah, concerning the distribution of the estimator itself, the fact that it is a truncated Gaussian. Imagine that you consider it as a truncated Gaussian. A truncated Gaussian, so the sum of variables following truncated Gaussians do not follow a chi-square distribution. Okay.
Okay.
And that is the reason why it is also not applicable here.
Okay, so maybe if you suppose that there is a full Gaussian, let's say, maybe your chi-square would peak at a negative mass or something like that?
Yeah, I'm not computing chi-square here, right? What I am computing, yes, I am computing chi-square. What I'm saying is that when you consider the distribution of this likelihood ratio, or the -2 log likelihood ratio, it won't follow a chi-square distribution if the parameters themselves are truncated Gaussians.
Okay.
Yeah.
Thanks.
Yeah, thanks. Okay, so actually your comment is good, because it is introducing the other topic I wanted to comment, which is, imagine setting limits near a physical boundary. So here, for example, the mass. I'm just taking the same example. So it may happen that this is smaller than 0. And in particular, it all may happen because, for example, how do you estimate the mass of something, of some object or particle or a system of particles, like invariant mass or whatever? You estimate like this, right? So you measure the energy, you measure the momentum, and then you subtract the two. It should come out positive, but due to the uncertainties in both quantities, it may happen that that your estimator comes out negative, and this is because it is not positive definite. This estimator here, right? Even though the mass is positive definite, the estimator is not because of your method to estimate it. No. So imagine that now in general. So imagine that I have an estimator of a parameter theta. So theta hat observed that I compute from data. Let me say it is -2. And I am assuming, for example, that the standard deviation of it is 1, just to put an example. If you take a normally distributed estimator, then you may compute a limit as we were discussing the other day, yesterday. So you will do something like this. Times the inverse of the cumulative of the standard Gaussian, right? So that was the formula of yesterday. Right, but then so fix confidence level. Typically using 95% because I know the number by heart. So I know that my inverse cumulative of this is 1.64 or so. Then this would be minus 0.35 or so. Right, so this is unphysical, of course, and you will like have you have like empty interval or something. Okay, right. So this is a problem. Okay, how do you solve, or how is it solved in the literature or in the community, in particular in the community of particle physicists? Then you have two approaches. For that. So the first one is to redefine your expression for sigma, for theta up, such that theta up will be actually, the first term will actually be the max between the observed estimator and 0. And then the rest of the expression remains identical. Okay. And that would immediately solve the problem, right? Because if your theta hat observed is negative, then you will just quote an upper limit, which will be in any case positive. So this problem you will solve it radically. But this is a handy thing, and many people use it. However, it is not good because it doesn't have the correct coverage of probability. No, it's going to be larger coverage. No, it's going to be larger. Right? Imagine if at 95% I get this amount of sigma up, theta up like this, then by this recipe here, I would get, I would actually get 1.64 because I have shifted the first term, and that would actually mean like a larger coverage than the one I am quoting. So people use this, but they are not anymore allowed to. It is not anymore correct to say that the upper limit is at 95% confidence level or whatever you tried to do before. Okay, so this is the first method. The second method is to go Bayesian, and I will discuss this later. But that's it. So I will discuss on the Bayesian part after discussing what is coming next. And the reason why I'm going to do something before going Bayesian is because it is still in the frequentist approach. There is this very convenient way or alternative to the classical intervals, to the classical Neyman procedure, which is the Feldman-Cousins procedure, or the Feldman-Cousins intervals. And this is what I'm trying to introduce you now. So what is the problem, or let me say, what is the motivation for that? The motivation is the following. The motivation is to solve something which in the statistics community is called this flip-flopping procedure. Flip-flopping or strategy, let's say. The flip-flopping strategy is the following. So imagine you have a model. So imagine you have a model for signal plus background. So this is the expected number of signal events. This is the expected number of background events, as we have already discussed previously. Okay, and then you measure, then you get some observed number of events. And then you say, okay, let me compare this. If the expected number of background events, it is actually very similar to NOPS. In particular, it is quite popular to say, okay, imagine difference is less than 3 sigma. I am talking now about Poissonian sigmas, okay? Then the flip-flopping strategy would say, okay, let us quote an upper limit for the expected number of signal events. Okay? Otherwise, let's quote an interval, not a limit. So the flip-flopping strategy is something that you say arbitrarily, I would decide if quoting or if computing an upper limit or an interval, depending on what I see in the observation, and then this is sort of arbitrary, right? So why would you do that? I mean, there is an arbitrariness here, and then this is the Feldman-Cousins is an alternative with you actually don't need to decide. So the Feldman-Cousins approach It's actually like letting data decide whether to quote an upper limit or on an interval. So this is one motivation, and let me this is also very it's a visual example I wanted to put in order to see this more concretely. So imagine that you have an observable. This be measured. This is a measured quantity. For example, I'm talking here about an estimator, let's say. Okay, let me put because of notation, let me just put something like this. Okay, so then when I say measured, I say that I measure my data and then I get my theta hat. Okay, so then the strategy would be, the flip-flopping strategy would be, if sigma hat, theta hat is smaller than 3 sigma, I will quote a limit, an upper limit, and otherwise I would go for the interval. And then the result of that, and then let us work at 90% confidence level. And let us assume sigma equal 1. So then I'm just comparing with in units of the standard deviation if you want. Then the confidence belt for mu, for the mean, or for the sigma, theta, sorry. I keep saying sigma. Is the following. Let me see if I found here the, yeah, it is this one. It is this result here. Okay. So I am assuming a Gaussian estimator. And then it goes the following way. So, I mean, that for every, for some measurements, I compute my interval, my confidence belt like this, right? So in vertical. For every value of x, then I can quote either an upper limit. So I quote an upper limit if what I measure is smaller than 3, and then you see that this is just an upper limit on mu. And if it is larger than 3, then you see that I am quoting here an interval, no? This is actually in the paper of Feldman-Cousins, okay? So in order to understand what is happening here, this value here, and also the other strategy in this plot is the fact that if I measure some value which is smaller than 0, then I pretend it is 0, and then I adopt this shift strategy here, right? So that's why I have a plateau here. It's a constant, and I have a constant because if it is -2 or -1 or whatever, then I just quote whatever the limit is corresponding as if it were 0. And this point here is the one corresponding to the 90% confidence level upper limit on a Gaussian estimator. And then once you go above 0, it goes up by the same amount, so it goes up linearly. I think this is something like 1.28 or so. So by going up, then you would add whatever value you get here, plus 1.28. And then you do this, and that's why you get this line. However, now let's say I'm measuring 3 or more. If I measure the 3 or more, then I go to the other part of the table. I don't remember. I think. Let me see. We saw the table. Yesterday. Yeah. Right. So I'm referring to this table here. So if I am below 3, I adopt an upper limit strategy. So I like take a look at this part of the table. So 90% is like 1.28 that I was telling to you. If I am above 3, then for 90%, then I am adopting this interval. I want to quote an interval corresponding to this part of the table. So it is this 1.64 or so. So this value here is actually 3 plus 1.64. And this value here is 3 minus 1.64. And then you go up in the observations, and then you, for every value that you observe, you like add 1.64 or subtract 1.64, and that's why this is what you get here. Okay. So this is the way it is computed. And then the problem here with this strategy, you see it. I mean, this is having actually not correct coverage. So it is actually, if you compute the coverage, I am not computing here, but it is going to turn out to be like 80% instead of the 90%. Mainly here. So I am this problem here is happening mainly here. So this interval here is having the incorrect coverage, for example. But in any case, everything is a bit arbitrary, and we wanted to get rid of this arbitrariness. So how does it work, the Feldman-Cousins alternative? The proposal is the following. So the proposal is simply to build the confidence belt as the region with the largest maximum likelihood ratio. This can be stated as simple as that. And then in practice, imagine that you have in practice, so the typical example that they give in the paper, and that it is quite visible there. So imagine that you have a model for signal and a model for background. So, but imagine that this is fixed. The background is fixed. So you want to make a statement on the signal, on the spectral number of signal events. So in practice, sorry, you compute the likelihood ratio, and n is this is a number of observed events. So you compute the likelihood ratio. This is Poisson, n given by S plus B, divided by the estimator, S plus B. I mean, this is actually the maximum likelihood estimator. And there is the estimator, which actually is the following. It's either 0 or n minus B. Okay? So the estimator is built like that. There is a shifted estimator then. This is imposing a physical constraint on S because S cannot be negative, which, however, is imposed in a way that will respect the correct coverage. Unlike the previous example where you were just shifting your estimator, here the whole procedure is solving this negative estimator problem in a way that allows you to compute the interval with the correct coverage. And then N here is varied in order to construct the confidence belt but what you do is such that what you do is to add progressively the values of N that in a decreasing order in likelihood. Sorry, in a decreasing order in the ratio. Okay. And you do this until the probability covers, in this case, 90%, for example. 90% of the Poisson distribution. Okay, so this is in words how it is done, but it is much better to see it in practice. So I have a notebook for that, which I will try to share with you now. Stop share. Okay, so let me share screen. Now, do you see my screen?
Yes. Yes.
But now I need to know whether I need to zoom in the, like, is this better or even?
We can see it well. I mean, we see the window and the background and all of that, but we can see it well. So it's not full screen.
Okay, so here better, right?
Yes, now it is full screen.
Okay, good. Yeah, so, okay, that was not the notebook I wanted to show. So is it good in size or I increase it?
It's fine, I think.
Okay, good. So yeah, I am, and this is something again, please, I mean, don't get lost in the details. I am getting this to you for your use. Just try to follow me here, what I'm doing with this algorithm. So first of all, what I'm doing here, since I am working with a Poisson example, is just to define what is the Poisson distribution. Given, so Poisson has one parameter, but this parameter is actually S plus B. So I have these two inputs separately. And the whole example is such that you fix your background and you want to make a statement on the signal, okay? Right, so, and then how do I compute the belt? So there is a known result here that it is in the paper. And the known result is the following. So the known result is imagining that you have measured expected number of background events to be 3, and you observe actually 7. And you want to make a statement about the signal at a 90% confidence level. Okay. Right. So for them, for that, I have written this function, which is a lot of It's a simple function, but it has a lot of comments for you to understand better. So I have this function which computes this confidence Feldman-Cousins confidence belt. And in order to have this function, I need to have a grid of values, like in the previous example that was in the previous part that I was showing you. In any case, this is the figure I want to reproduce, right? So this is the paper of Feldman-Cousins. I'm trying to reproduce this figure here. So in order to reproduce this figure, and the procedure is to have a grid of values for the measured number of events, and a grid of values for the mean, or in this case, the signal, right? So this is the signal mean. Of course, this grid in the vertical axis is not the integer, so there are many values in between. So because this is a real number, okay. So this is why I have these two grids that I compute, and actually, my first grid is just some equally spaced points between 0 and 15. Sorry. This is for the n, from between 0 and 40. So I just have a 0, 1, etc. until 40. Whereas my grid for the mean has around 3,000 elements from 0 to 15. Okay. So I have a very fine grid for the mean, and I have a grid of number of observed points from 0 to 40, but I mean 40 is probably too much. And then, so this is those two grids I need, those two arrays, if you want, I need. And then B is the expected number of background events that is fixed. This is the observation, and this is the the significance of the test. Is alpha. So alpha in this case would be 0.1. Okay. So essentially what I'm doing here is the following. I compute for every n here. Let me go back to the paper. For every n here, I compute. I consider the likelihood corresponding to all the points for a given for all each of these means for each of these mu in this notation, and then I choose the point given the maximum likelihood, and I keep this maximum likelihood point, and I do this for every n. So I have for every n, I store in a variable the maximum likelihood given by one of these points, let's say. This is what I'm doing in this part. So I'm just computing the Poisson distribution for a given n for all the points of my array of mu's, and then I get the maximum. And I save it in a list. Now, now I go and then I make a loop over the mu's, over this array of means. And what I do is that for each value of mu, so let me go back to the paper again. So now I'm moving in a horizontal axis. Then I can compute the value of the likelihood ratio corresponding to each value of n. So I move n equals 0, n equals 1, etc. And for each of these values, I can compute the likelihood ratio. Because first of all, in the numerator, I can just evaluate the likelihood. And the denominator I already have because I have stored before the maximum likelihood associated to a given value of n. So this is what I'm doing here. So in this way, I have stored, after doing this, I have actually for every value, for every point of my grid, I have a value of likelihood ratio. These are quantity here. Fine. What do I do then next? So what I do next is to sort these values in descending order and keep the indices. So this is just a way to keep the indices of the sorted values of R in a descending order. And I start computing my p-value. My p-value is computed by adding evaluations of this Poisson distribution for a given mu. I am still inside this loop of mu. So for a given mu, I start adding the Poisson distributions, but I start by the values of n given the largest R. Okay, and then I go here in descending order, etc. I do this until a point where the p-value is equal or larger than 1 minus alpha, because this is the condition to exit. Okay, and then I save the result. And that's more or less it. So grosso modo, this is what the algorithm is about. And then if you do this, I reproduce this thing. So how to compute from these two curves the interval? So this interval is produced independently on the observation. So these stairs here, these blue and orange stairs, this is independent on the observation. But now you want to say, okay, let me see what comes out, either an upper limit or an interval, because in this way, this is not something I decide ad hoc, or not something that I decide like in an arbitrary way. It is coming naturally out of this procedure. So once I have these two lines here, if you want, then I put my observation here is 7, right? So if it would be 4, then what comes out is an upper limit. If it would be something less to 5, actually, I would have gotten an upper limit, but instead, after 5, what I am getting is an interval here. So then the rest of my function here that you can go to understand later is to compute these intersections here. Either this one, or if it is an upper limit, only the intersection with this one. Okay. Is there any question so far? And actually, this figure is pretty identical to the one of the paper. So you will have like a working code, allowing you to compute Feldman-Cousins, at least for this simple case, but then it would be straightforward to adapt to another problem, hopefully. Questions?
I have a question. So,
yeah, tell me.
How do we plot the orange line?
Yeah.
Sorry, I got lost a bit.
Yeah. No, you don't. You didn't get lost. I didn't explain.
Okay.
Yeah. So how do I plot the orange line? So imagine that I have now arrived to the point where I am covered. Okay. So I have arrived to, let's say, 90%. Then I am saving the following thing. So I save two quantities for a given mu. I save two quantities, n min and n max, right? So n min and n max are just, so for a given mu means I am moving in the horizontal direction. So I save n min and n max given by, so imagine that I have considered this p-value, this construction of p-value was considering all the n's inside this interval, right? So imagine that mu is 2. Then by sorting the values of the likelihood ratio, I have then added Poisson probabilities corresponding to the values of n inside this interval. So I have started, let's say, here, and then here, and then here, etc. So, and just in a sorted way, it will be depending on the indexing of the sorted array. But it will be there will be one n in this interval which will be maximum, and that would give me the orange. It will be one of these n's will be which will be the smallest of all of them, and this will be my n min. So then, wait, this is not. So n min is the minimum in this array where I actually I consider all the n's entering because I have sorted my values of the likelihood ratio. Then I will have with this object is giving me the smallest n corresponding to this sorted array. And I get then I will get then the blue point, so a point in the blue curve. And by doing analogously, by instead going and take the maximum, I will get a point in the orange curve. And I have done this for a given value of mu. So I am doing this for all the values of mu, and that's why I'm getting the orange curve and the blue curve. So let me, in order to be more clear, let me execute this, but I am printing a very large thing, which is the indices of the sorted array. So let me modify the function such that it prints this this result. So it means for the first value of mu, because I'm I am now inside the mu loop. For the first value of mu, I get these are the sorted values of R, the indices, right? And the indices, when they sorted, it came out in a natural order for the first value of mu. So actually, the first value of n is giving me the largest value of R. The second value of n is giving me the second largest value of R, and so on. However, look at what happens in the second value of mu. The second value of mu, the first n was not the largest, was not giving the largest ratio, was the fourth. And then, so you see what, I mean, this is the index of the array in n, in the number of observations. So this is giving me the order where, okay, I need to sum the fourth. I mean, this is zero base, right? So this is the fourth value of n plus the third plus the second plus the first. And then in the sorted array, I need to go to the fifth value of n, to the sixth, etc. And I do this for every value of my 3000 values of mu. And some, I mean, there is they change from time to time. For example, here, the sorting is different. Then here, the sorting is, sorry, the sorting here is different. So it really depends on the value of mu, right? And it is keep changing. Actually, it's changing in a systematic way, changing by 1 unit. So is it more or less clear, this part, or
Yes, I think so.
Okay. I mean, anyway, I will, what I'm doing, I'm trying to go up, but I'm confused about. Okay. This
So
is so
one more
easy.
question.
Yeah.
So whenever this changes, we have this difference in the plateau this time or no?
Oops. I don't know what happened. Do you see my screen or not?
Another notebook.
Yeah, sorry. Yeah, tell me the question, please.
So whenever this changes, when we sort the indices,
Yeah.
is this the change in the plateau that we see, that it goes up?
Yeah. Let me reproduce this without the full thing. Yeah, so then, yeah, exactly. These jumps are
Yes.
are given by this, exactly.
Okay.
Yeah. Any other question here? Okay, if not, let us move on then. What I'm doing? Stop share. Start sharing. Okay, that was Feldman-Cousins, and I think that many people today they use it directly in order to avoid this flip-flopping policy strategy. And now I finally go back to what I wanted to tell you about Bayesian. This is called credible intervals. Okay, so the idea here is to make use of the posterior distribution. So you make use of the posterior distribution of your parameter of interest given your data, and you make use of it such that an interval, let's say theta between theta low and theta up, let's say, is determined as, so you fix your significance of the test, and then you integrate between theta low and theta up, just integrate the posterior distribution. So interpretation here is natural, because I mean, interpretation here is just the region where the true value of the parameter is contained with certain probability. So that would define a region, right? In general, this is a region for also for multivariate case. This is a region where the true value is contained with certain probability, or if you want to use the jargon, you put degree of belief. This is the Bayesian jargon, right? And note, this is a completely different interpretation, different from the frequentist one. What was the interpretation of the frequentist one? So it is like a weird thing, weird interpretation. If the experiment were to be repeated, right, many times, and then, of course, that requires the same initial conditions, all identical experiments repeated many times, then the then the true value would be contained in that region or in that interval, a fraction 1 minus b of times, let's say. Okay. So this is the interpretation of a frequentist interval, but it is a weird thing, no? So it is easier to just interpret the Bayesian, the credible intervals in that sense. It is natural. This is what you may get, and actually many people are confused, and many people interpret the frequentist in a Bayesian way, but they are, I mean, the interpretation is wrong, actually. So the interpretation here is the one that you may naturally have in your mind. And imagine you want to do an upper limit, for example. In practice, you do the following. So there is 1 minus beta from minus infinity to theta up of your posterior. Let me just call data x vector. And in practice, you just do, for example, you just take into account the numerator of the Bayes theorem, because then you normalize it afterwards. This pi theta is your prior, and then the normalization, it is just the integral over the whole range of the thing on top. Okay. Sorry, no, there is no vector here. So in practice, this is what you do. So what about the prior? This is another, of course, this is a typical issue with the Bayesian approach. Then what do you say by the prior? Actually, the prior will be helpful because it will allow you to implement like a physical constraint. For example, I can define my prior to be 0 if theta is less than 0, or 1 if theta is larger than 0. So it provides a solution to the physical boundary problem here, no? Of course, I mean, the result will be prior dependent, etc. And there is a more elaborated discussion in the Cohen's book. But this is a way to naturally implement the physical constraint and to actually to get a limit or an interval, sorry, in general, that is consistent, that has good coverage, etc. Sorry, in practice, then what they do, so what you do when you want to implement a credible intervals, so you implement it in a way, so such that the points of the posterior inside the interval are larger. I mean, the values are larger than outside. And this is more or less what you actually do in practice with the Feldman-Cousins, right? So you imagine you make a grid of points. So let me now put a plot here, like two-dimensional in general. So you have two parameters, you want to build a confidence region. So you have a grid, no, of points, and for every grid of points, you just compute the value of the posterior. You evaluate the posterior in this parameter, and then you just choose the region given the largest posterior. So, and because how do you where do you stop? So you add the values of these points. So now let me put a vector because I'm two-dimensional here. So you add the values of these points until the probability is equal to your confidence level. Okay, in the very similar way that we did for the Feldman-Cousins. So that is a practical way to implement Bayesian credible intervals, and that's pretty
One
much.
question?
Yes.
Sorry.
Yeah.
So is it similar if you have a one-dimensional one parameter, let's say, and you plot the posterior?
Yeah.
Is it the same of having a threshold and moving it from the upper bound of the posterior until you reach the confidence level?
But the problem is that the problem that I see here is that you imagine that I have one parameter, no?
Mm-hmm.
And imagine that my posterior is
Yes.
something whatever, okay?
Mm-hmm.
Then what I do is to sort, because if you don't sort, so if you sort, and then you will start adding this first, this later, or this, then you start like, right, going in this direction until you cover 90%. If you don't do this and then you start like in increasing order in theta, you say?
No. I mean in the y-axis.
In the y-axis, okay.
Yeah, to have a like a horizontal line, let's say perpendicular to the y-axis, which is larger than the maximum of the posterior, and reduce it until you reach the confidence level under the curve.
So like moving,
yes,
like this.
Yeah. Yes.
I think it is the same.
Okay.
Yeah, it is. This is actually what it's a strategy. It's like similar to the annealing thing, optimization, simulated annealing optimization. I think they do this. Yeah. Okay. So if there is no more questions on this part, I would like to make a pause here and then change topic after a 5-minute break, if you don't mind. Is it okay?
Yes, yes.
Okay, so let's meet at 12 past 12, actually. See you now then. Okay, so let us continue, if you don't mind. Let me share screen. Do you hear me?
Yes.
Yes, we can hear you.
Okay, thanks. So we will just start and hopefully finish today the next to last topic of these lectures, which is model selection. Oops. Model selection, not only frequentist, but also Bayesian. So in order to do that, let me just put an example, and this is just going to be an image. Something went wrong. Okay. What was that? Yeah. So, okay, this is something I did some time ago. So I took some data, generated some data with some error bars, whatever. And I am fitting for each data a polynomial of degree 3, given by the red line, of degree 5, and of degree 8. So by looking at this plot, what would be for you the best model? This is going to be the third order polynomial, the fifth, or the eighth order polynomial. What would you think?
The third?
The third. And note that the green one fits the data better, actually.
But it has more parameters, more free parameters, and it's overfitting or whatever.
Okay. Yeah. So and the reason is, I mean, the reason, the underlying reason is that I mean, intuitively, you don't think that model 8 is the model, is the underlying model that have generated this data. So which is actually what you are after. I mean, this is ultimately what we are after in statistical inference. We want to make the generating function or the underlying distribution of the data that we are observing. And indeed, model 8 is sorry, fits data better, but is doing overfitting. Okay, so somehow the whole problem of model selection is to find a model which describes the data well enough. But I mean, you want also to avoid doing underfitting, right? So here the idea, find a model describing data well, reasonably well, while avoiding not only overfitting, but also underfitting, right? I mean, I have a model here, which is given by a constant, and that would underfit my data. I mean, it is a simpler model, but would underfit my data as well. So this is like the whole thing in model selection. Or, I mean, there are more things, but this can be expressed in these simple terms, if you want. So one of the most common ways to compare models, I mean now put like a model comparison or model evaluation, let's say. A very simple way is to look at the chi-squared over degree of freedom. You look at this quantity. And the justification for that is just based on what we saw previously, right? So that using the chi-square as a goodness of fit. So imagine that you have some observations. So imagine that I'm observing some series of y. They follow a Gaussian distribution. And I am modeling that Gaussian distribution by a mean given by some, I am observing y as a function of x. So I am modeling the Gaussian, the expected value of this y by a mean distribution, a mean function, which is depending on the input, of course, but some parameters. So let me just say this is a set of m parameters, the number of parameters of my model. And then imagine I have known standard deviations, for example, given by the experiment, the experimental measurement. No? If this is the case, then I build my chi-square as this sum over all data points, yi minus mu I divided by sigma I, everything is square, and I mean, you know that this follows a chi-square distribution. Hopefully follows. I mean, in the sense that you need to ensure the applicability of all these, like not having too few values, etc., as before. But it follows a chi-square distribution with now n minus m degrees of freedom, because I am fitting now m parameters. So this is just a number of fitting parameters. So in a way, this chi-square is like a measure of how likely it is that data comes from the model whose predictions are given by mu I in units of standard deviation, right? So then also note that the mean of this distribution is given by the number of degrees of freedom. So it makes sense to write something like a rule of thumb given by, so if this thing is much larger than 1, then I have really a bad model. And this is a model that doesn't describe well enough the data and is very poor. So I have a case of underfitting, let's say. The model is not complex enough. So you are actually doing a very case of underfitting. And the model is reasonable when chi-square over degrees of freedom is similar to 1. So the fit is reasonable. In other words, I mean, if chi-square is over degree of freedom is similar to 1, it means that all the predictions here that I am doing for all the points, they lie within one standard deviation, something like that. Okay, so this means that they are reasonably good. And if it is much smaller than 1, either I am doing overfitting, or I have overestimated my my errors, my uncertainties, because that would mean that this denominator here is very large, so you would get I mean, like a very low chi-square over degree of freedom. Okay, so this rule of thumb actually has some disadvantages. So it has some drawbacks here. And imagine I compute this thing for one model, and it turns out to be similar to the chi-square over degree of freedom of another model. They are both close to 1, okay? So then what model to favor? What model would you choose? There is an even more serious disadvantage of that. So imagine model 1 gives chi-square equal, I don't know, 15, and I have 10 degrees of freedom, whereas model 2 has a chi-square equal to 150 with degrees of freedom equal to 100. So in this case, both models will have the same chi-square over degree of freedom. However, the p-value of model 1 is something around 1.13, whereas the p-value of model 2, it would be something like 9 times 10 to the minus 4, right? So, I mean, you cannot really, there is some loss of information in doing this ratio here that that is inconvenient in some circumstances. And the third drawback here, the third disadvantage is that if data is clearly not normally distributed, I mean Gaussian, then the conclusions will be maybe incorrect. Okay. So then you go to another more like efficient approach, which is, so this is alternative number 1. I don't know how to put this. Alternative number 1 here. Alternative number 2. And then the alternative number 2 is to divide data, to split data in training and test. So then with this, you do the fit of the parameters of your model. And you do this for every model, for all models. While with this, you test the models. And going back to this figure before, clearly, if I have here some new test data, imagine that I have some test data here, then obviously for a test data here, the green model will not give a very good answer, while the other two models, I don't know if it is here, will give better answer, okay, better prediction, smaller error, let's say. So, and also, and also here, I don't know. So if you have a point here, obviously model 8 will just go off by a lot. And this is what is typically done in machine learning. Community, let's say, okay? The practice. So this is also, just to be clear here, this strategy is also an heuristic, like the one before, but it is more powerful than the chi-square over degree of freedom. And actually, it is more powerful because by computing the discrepancy between data and predictions, I mean, so why is that? So you are actually choosing the model giving largest likelihood in the corresponding to the test data. This is what you're doing actually. So you can actually choose a model. Of course, I mean, if two models, they give close likelihood in the test set, in the test data, okay, both models will be more reasonable, but you can give an answer to that. Whereas in that rule of thumb of the chi-square over degree of freedom, you couldn't. It is not a bit better to have a chi-square over degree of freedom of 1.2 than 0.98. So it is really, you have less control of that. While here, you can evaluate your likelihood, and if the likelihood is better, even just a bit better, you can actually state, okay, this is the best model. But also, the method is not restricted for sure to Gaussian data, sorry. To Gaussian data. And actually, it turns out that, I mean, you typically will have plots like the following. Let me see if I find a plot, the plot I wanted to show. I have lots of images here. Yeah. So you have something like that. I am now computing the error, or this is like a mean square error on the test data. And I am evaluating this for every order of the polynomial numerical, linear, quadratic, cubic, etc. Here for that, for the data actually that generated the plot above. And then I evaluate the mean square error on the test, on the train, and on the test. And what typically happens is that you start with larger values of the error here. So you have in this region, what color I use, I don't know. In this region here, this is a region which is clearly underfitting. It is a region of it's too simple model. Whereas in this region, you are clearly overfitting. Because even though you are describing the training data better, and that is reflected in the fact that this is always going down, you will perform worse and worse in the test set. So this region then here will be the optimal region, the optimal model complexity, if you want, or the optimal model. I mean, I am a family of models which are all the polynomials that I can imagine, and I choose which polynomial is the best, or all the whatever other non-linear model that you can imagine. I have a catalog, and I plot for each of them this thing, and then I choose the best one. Okay. So there is a drawback here. There's another disadvantage here is that it may not be convenient for small data sets, for very small data sets. And why is that? It is just because if a data set is very small, then you may not have sufficient training data in order to fit your model. Because you need to spend some of this training data, you need to separate it, you need to reserve it for the end. And then, but if you have too few points, then you may not fit the function correctly. So that is the whole thing. Okay. That is the whole reason why it is not a good strategy for small data sets. Anyway, so note that when the model underfits, so this is a separate thing. So if you have underfitting, then here it means that the bias is large. Like here, imagine I have an underfitting because I have a linear model. So I have something like, well, I don't know, something like this. That is having a very large bias because the expected value here, I mean, will be always separated from the true, right? Value of the model. So that's why underfitting is also characterized because of your having a large bias in your predictions, while the variance is very small. And overfitting is the opposite. Overfitting is giving you low bias because the difference between the prediction and the training point is very low. But of course, you have a very large variance. You have these wiggles, you have going up and down depending on the training. It follows too closely the training data. And then there is the sweet spot here is in between, right? So it's something that you need to there is like a trade-off between the two. And this is actually has this name of bias variance trade-off. So a good model will have a good trade-off, a trade-off between bias and variance. Right, so let me just expand a little bit on that. So imagine, so you have, for a model, you have the mean square error. So the mean square error is just this, yi minus mu I squared. So it can be shown that this is actually a combination, it's a linear combination of bias and variance. Okay. The way to do this, the way to see this is nothing. So imagine that you have some observations y, which are a function of x, and you want to model this by a function f. Plus, you consider some noise here, where the noise is following a normal distribution with zero mean and some variance. And that would imply, by the way, that this data is following a Gaussian distribution with mean given by f and variance given by the same variance. So then what you do is to compute the variance of this. So let me compute the variance of my estimator here. And then by definition of the variance, this is just the expectation value of the square minus the square of the expectation value. And the bias is the expected value, expectation minus the true. So what is this expected value is about? It's just taken with respect to different data sets. Different possible data sets one could have access to. Okay. And then you just like a priori, I mean, in general, the mean square error is just the expected value across data sets of these quantities, right? This, of course, evaluated in a new point, like unseen before, like our test point. Right. So then there is it is a very nice exercise of computing this. So y is given by f plus epsilon minus f. Like this. And then the idea here is to like develop this thing, doing the algebra for computing this. So you open the square and you compute the expectation with respect to, I mean, of all the terms. And when you do that, I mean, this is just like I have 5 lines of algebra. When you do that, then you get the following. You get f minus expectation of the value of the estimator plus expectation of epsilon square, right? I'm just to put in like intermediate step. You get this minus this square. And this is finally just nothing but the bias square plus the variance plus, of course, the irreducible error, which is sigma, given by this term here. Okay. So I didn't do it the whole steps, but I mean, this is just 5 lines of algebra. It is everywhere, including Wikipedia. So anyway, so this just to say that the mean square error that you are minimizing when you want to choose the best model is actually a combination between the two, and of course you have a combination where they are very too simplistic model. This will be very low, but this will be huge. And a too complicated model this will be very low, but this will be huge. So you have a trade-off here. Okay, so any question? Fine. Let us then go to the final part, which is Bayesian model comparison. So far, I have been talking about frequentist model comparison.
Well, I have a question, maybe.
Yes.
How do you decide how to split your data into test and training?
Mm-hmm. Yeah.
Like, does it have to be a random process, or
yeah,
and do they have to be disjoint?
Yeah, no, the critical thing is to the critical strategy here. So imagine that you have your data here. This is y as a function of x, and then the critical thing is that imagine that you cover. So imagine that the true underlying generating function is something like that, okay? The strategy for splitting training and test is such that you have the training should cover all the range, and also the test should cover. So both of them should cover all the range. Okay? And this is done like this because imagine that you like separate this part, I will do training on it, and this part I will save it for test. Then obviously the model is going to predict whatever here because you are fitting the model with the train. So you're like fitting the model with the incomplete domain of your input, and then the predictions will not be good in general here. And that's why you need to distribute across the whole domain, not only your training data, but also your test data. So this is the test, whereas these guys are trained. Okay. Is this answering your question?
More or less, but my question is also, for example, like I know some people, when you don't have enough data, you can do stuff like fitting the function to all points except one, and then checking the chi-square with all points and stuff like that. Can you do this also in this approach that you're suggesting us? They have to disjoint.
What do you mean by disjoint? Sorry.
That the points go either to test or train, but you cannot have a point that is in test and train at the same time.
No, this is also the plot I'm showing here. This is disjoint.
So it has to be disjoint.
It has to be disjoint. If this is what you mean by disjoint, yes, of course. One point you is either test or train, but it cannot be both.
Okay, thank you.
Okay, so any other question? Okay. Yeah, I was about to start talking about Bayesian model comparison. So let me write an expanded version of the Bayesian theorem. I have a posterior of a model of a set of parameters belonging to a given model, and I have data as well. Right? So this is given by the likelihood of the data given by the parameters of the model times the prior of the parameters corresponding to that model divided by the evidence, which is the probability of data given a model. This is called the evidence, okay? Obviously, for a different model, I will have a different set of parameters. They have nothing to do. Sorry, they have nothing to do, and then it is obviously that there is a model dependence here in this expression. Okay, so now suppose you have two models. So suppose two models. Let me call them M1 and M2. Then I can write the probability of model MI given data, which is nothing, which is not equal to any of these objects I have written before. This is another object, like a more generic object, let's say. This will be proportional to the probability of data given the model times the probability of the model, the prior of the model, okay? So this is my let me say, degree of belief that this model is correct. This is here the evidence. And this is the posterior of the model itself, not of parameters of the model, but the posterior of the model itself. So imagine then, that you adopt an assumption that that the two models are equally probable. So the prior of the two models are equal. Then the idea is to compute the ratio between the two posteriors which under the above assumption, it is just given the ratio between the evidences of the two models. Okay? So this is a ratio of evidences. Evidence ratio. And this expression is the so-called Bayes factor. In the literature, it is called Bayes factor. Okay, and then you compute the Bayes factor for that. Imagine that you are able to compute the evidence because you have a very good computational tool for that. And then there is a criterion. So which criterion is you use? So there is a criterion by Jeffrey. So there is this Jeffrey scale, where according to the value of this Bayes factor, let me call B. According to the value of this Bayes factor, you would actually say that, okay, imagine that my Bayes factor turns out to be -1, then I will have a negative, let me put it, strength of evidence that I am actually favoring model 2 against model 1, right? And if it is between 1 and 3, it is like very worth mentioning. And etc. So if it is between 3 and 10, it is unsubstantial, but it is an arbitrary like scale, arbitrary criterion, but people use it. From 10 to 30 is like strong. Then I don't know. I just completed the table. Very strong, or larger than 100 is like decisive, right? Anyway, so this is the whole point about the Bayes factor. So it's about comparing the models in the Bayesian way is just to compute the evidences. But I mean, let me, in order to get more insight on this, let us suppose the following. So I have a very concrete example. So imagine I have a very simple example of one single parameter. Let me call this parameter W. And then suppose that the likelihood of my data is like sharply peaked around some value having a small width equal to delta W, okay? Also imagine that I have a flat prior for W. So if I have a flat prior for W, it means that, okay, prior is 1 over some window, delta W. Let me just put here prior, just to make just to be clear. In this very simple situation, then let me try to draw here a cartoon where I have my likelihood here. Okay. So this will be then centered at W hat, and I have this width, right? And then I need to compute my, so I need to multiply this by my prior, and my prior is, I don't know, this flat prior in this window here, where the width of this is given by delta. This is the prior, a uniform prior given by 1 over delta W. Then, if this is the case, I can write an approximation to the posterior of the model. Yes, so an approximation to the posterior of the model. So this is data given M. This is equal to P. I mean this. The probability of the data given the parameter times delta W divided by this the prior. I mean, because the prior is 1 over delta, so I have this. Okay. So it is just a multiplication. So I'm just considering here the very simple assumption of a very narrow probability. So now assume for a model, I have a imagine that I have k parameters. But before, sorry, before I go to more parameters. So here, obviously, I have a penalization for models having large prior uncertainties. And this is something coming out of the Bayesian model comparison. So if you put like a very large window in your flat prior, or if your prior is a Gaussian with a very large variance, that would be that would penalize actually the evidence, let's say. Okay. So now imagine that I like sort of repeat the same sort of reasoning, but now assume a model with k parameters. So I am now considering a generic thing where a generic situation where I have k of these parameters. Let me just suppose similar ratio of the following. And just to simplify the argument. So I'm just assuming this is equal to the same quantity for all the parameters. Then the evidence of this model will be similar to before times the prior of all the parameters, right? But the prior of all the parameters, according to the above, is just this thing. Is it that you follow this, or there is something that is not clear in what I'm doing?
I have a question.
Yes.
So in the first equation that we wrote, this one, so you approximate the integral by of the evidence, right? By this.
Yes, I approximate the integral of the evidence because it is sharply peaked the likelihood.
Okay. And the prior is 1 over delta.
Prior is 1 over this thing.
Okay. Because
So,
it's uniform.
It is uniform, so it goes out, and
Okay.
then the integral of the likelihood is like a rectangle. So width times height.
Okay, I see.
Yeah, sorry if it was not clear. Yeah.
It's fine.
And I'm doing the same here. So I am approximating here in the multivariate case, I am approximating the integral of the denominator of the Bayes theorem by the height times the width of all the parameters. But then I multiply by the prior is 1 over the capital delta, and then I have this factor here. So this is actually, I wanted to have blue. This is actually a penalization for models having too many parameters, right? The more parameters you have, the larger, the smaller will be this factor here. Obviously, this factor is smaller than 1, so something smaller than 1 to the to the k power is something very small. So in general, this Bayesian model comparison is penalizing models which are too complicated. Obviously, if the model is very complicated, this likelihood will improve, of course. You will fit the data better with a more complicated model. But then there is a trade-off between improving this factor and getting this factor worse. So in a way, there is a trade-off with improving the likelihood term. So this very simple analysis here is just giving you like a flavor of what Bayesian model comparison is doing. So it is on the one hand, penalizing models where you're uncertain. If you are very uncertain about your prior, then this is a penalization. And on the other hand, it is a model penalizing too large values for too large models, too parameterized or with too many parameters.
Sorry, one more question. So in this expression with where you say to the power of k, is this valid, or you have to use different omegas there?
No, I mean, I am assuming that for all the parameters, I am assuming that this ratio is the same.
Okay.
If not, I would have in general like a.
Oh, I saw that now. Sorry.
I have a product now. Yeah.
Yeah. Sorry.
Yeah, but I was just simplifying this in order not to put a product here. I was.
Right.
Yeah. But in general, it's just this product over all these factors, right? Right. So this is about it, about Bayesian model comparison. The only thing I will just comment is the obvious drawback of this technique is that computing the evidences is, in general, intractable. It's an intractable problem, and then you rely on approximating the evidence. And this is the whole domain of approximate inference in variational in the variational community. Inference techniques. techniques. Okay, whatever, I forgot how to write it. Okay, so this is the whole thing. Of course, you if there is a computational way to do it and you believe that your approximations are very good, then this is the way to go. Any questions so far? I mean, so far not. Any question for the whole lecture, etc. Because we are done. Okay. So if not, let's close here, guys, and then let us meet tomorrow for the last